In this section, we're going to study the reactions of ethers. As you may remember, alcohols can be protected by forming ether. Okay, so here is trimethylsianyl ether, and this ether is unreactive under many chemical conditions. But this bond can break if acid is added to go back to the alcohol. Similarly, ethers involving carbons are generally unreactive, and the two types of reaction we are going to look at. One is acidic cleavage, and the other is Claisen rearrangement. Under acidic condition, such as hydrogen iodide, hydrogen bromide, the carbon-oxygen bond may break, given alcohol and alkyl bromide. This reaction is the opposite of valence ether synthesis, where alkoxide reacts with alkyl halides and give you an ether. And in the ether cleavage reaction, the smaller side becomes alkyl halide, and the larger side becomes alcohol. In this case, it's a phenol. Let's look at the mechanism of acid cleavage of ethyl isopropyl ether. As usual, in acidic condition, oxygen is protonated by hydrogen iodide. The hydrogen iodine bond break forms an iodide, and the ethyl isopropyl ether forms a protonated intermediate. The next step, the iodide from the first step serves as a nucleophile to undergo SN2 mechanism, attack the smaller side carbon. In this case, the right side carbon is primary, and the left side is secondary. So the iodide attack on the right side, and the oxygen-carbon bond break, and the oxygen-hydrogen combine with the left side alkyl group forms an alcohol. In this case, is isopropyl alcohol. On the right side, the iodine combine with the alkyl group forms iodoethane. And this mechanism explains why the smaller side forms alkyl halides and the larger size combined with oxygen forms alcohol. And note that in this molecule, we have a primary carbon and a secondary. So right side primary, left side secondary. If the ether contains a tertiary, then the mechanism will be different. Here shows an ether molecule that contains a secondary and a tertiary carbon. And under acidic condition, the molecule undergo SN1 or E1 elimination. So the carbon-oxygen bond break, the two electrons goes to oxygen, and the right side becomes a carbocation. And the left side oxygen combined with alkyl group give you the alcohol. And the right side carbocation either combine with the alkyl group forms the alkyl halide, or it undergo elimination reaction to give you a double bond. Okay, so in this case, the smaller side becomes alcohol, and the larger side becomes alkyl halides or E1 product. And this is opposite as we shown in the last slide for a molecule that only contains primary or secondary, no tertiary alkyl groups. Practice: predict the products of following reaction. And this is an acid cleavage of an ether. In this type of reaction, if the ether contains only primary or secondary alkyl groups, the reaction is SN2 mechanism. The halides attack the smaller side, so the smaller side forms alkyl halides, and the larger side forms alcohol. But if ether contains tertiary, okay, so in this case you have a tertiary carbon, then the reaction is undergo SN1 or E1 reaction. So in this case, we predict this carbon will break because that forms a carbocation. So tertiary carbocation, remember, tertiary carbocation is stable, so it's favorable to form. And therefore, this oxygen goes with the right side, the smaller side. Okay, the smaller side forms alcohol. In this case, is 1-propanol, and the left side combined with the bromine forms 2-bromo 2-methylpropane. Okay, of course, this reaction may also have elimination, so you may form double bond also. In summary, ethers undergo acidic cleavage reactions. A tertiary alkyl ether undergo SN1 reaction. The carbon-oxygen bond break forms a tertiary carbocation. The oxygen goes with the smaller side, forms an alcohol, and the larger side forms alkyl halides or possibly E1 products. For primary secondary alkyl ethers, the reaction is SN2 reaction. Halides attack the smaller side, forms alkyl halides, and the larger side goes with oxygen, forms an alcohol. As we have shown so far, ethers are unreactive and only undergo a few reactions. One is acidic cleavage of ethers. And here we will show another type of reaction called the Claisen rearrangement. And this reaction is specific to allyl-vinyl or allyl-aryl ethers. Allyl means a 3-carbon with 1 double bond. So this is a allyl group, and the vinyl is a double bond. So add oxygen, and this is allyl vinyl ether. Aryl means benzene ring, so allyl aryl ether. Okay, now here shows allyl aryl ether, and this Claisen rearrangement is a concerted pericyclic 6-electron reaction. All right. So what that means is, if we start with this double bond, the pi bond move to here to form a new bond. At the same time, the next pi bond break goes to the next bond to form a new double bond, and the next single bond break, 2 electrons to go to here, form a double bond here. Everything happens at the same time through this transition state. Well, the new bond is almost to form, a old bond almost to break. So a new bond almost form, new bond almost to break, and new bond almost to form. Everything happens at the same time. With the transition state involves 6 electrons, 6-membered ring, and then here is the product. Okay, so I would suggest you try to move electron as shown here and see if you can get this product. Okay, so this product is called gamma delta unsaturated ketone, and this is the ketone, and this next carbon is called alpha carbon, and this is beta gamma delta. The double bond is on the gamma delta, so that's called gamma delta unsaturated ketone, and that's the product from Claisen rearrangement. Okay, now in this particular case, we can see the reactants is a benzene ring, but the product has only 2 double bonds. So in other words, the product loses aromaticity. This is not favorable. So in order to resume aromaticity, the product undergo a hydride shift. This hydrogen goes to the oxygen, and the pi bond goes to this bond, form a double bond, and that will resume aromaticity, and the product is actually a phenol. Okay, note that this last step is specific to this case, okay, to resume aromaticity. Usually, and here is the product from Claisen rearrangement. That's called alpha or gamma delta unsaturated ketone. Here shows an example of allyl-vinyl ether. So this is the allyl group, and this is the vinyl group, and this molecule undergo Claisen rearrangement. And we can start with this pi bond. The pi bond move to the next here, form a new carbon-carbon bond, and this pi bond move to the next one, forms a new pi bond, and this single bond break goes to here, forms a double bond. Everything happens at the same time through a transition state, give you a product which is gamma delta unsaturated ketone. Okay, now this allyl ether undergo Claisen rearrangement you already see in the last slide. Okay, that's the product. Again, it's gamma delta. Well, in this case, it's a phenol because the hydride shift to resume aromaticity. Now, this shows how to make this allyl ether. Okay, we start with the phenol with a base. It deprotonate from phenoxide. Okay, the phenoxide undergo SN2 reaction to attack this allyl bromide, and that will give you allyl ether. Exercise. Propose a mechanism for the following reaction. Now let's look at the reactants. This is an ether with a allyl group, and the left side is similar to allyl group, but with a triple bond. All right, triple bond is 1 pi bond more than a double bond, so it's similar to allyl group. So this structure suggests that the molecule may undergo Claisen rearrangement. So the pi bond, okay, so this pi bond move to here, form a new bond, and this one of this pi bond move to here, form a new double bond, and this bond break goes to here, forms a new double bond. Okay, so this is the product, and note that a triple bond after 1 pi bond move, it still have 1 pi bond, so it's a double bond, and therefore this carbon connect to 2 double bonds, and that's not stable. And in order to stabilize the molecule, the product undergo a hydride shift. Here is a hydrogen. This hydrogen shifts to this carbon, pi bond shifts to here, and that is give you the product, which is the final product. Here are the homework problems.